Okay, we're going to take a look at yet another problem. Now I've tried to go through and select some of the ones that I think would be most challenging and to shoot some of these videos to go along with them to help out. Now one of the ones that I almost didn't assign but figured I should and to go ahead and do a video for is one in which we have several forces being applied onto a car to make the car move. Now, my question says two forces, 444 newtons at 10 degrees and 382 newtons at 29 degrees are applied to a car in an effort to accelerate it. Now they have a diagram to go along with this. I have a one personal notation. I would say that it would be better to say 382 newtons at negative 29 degrees for my drawing. Now what they've got is I've got a drawing of a car, and it is marked that it is 3,207 kilograms, and that there is one force, which we have pointed out like this, which is 444 newtons. If this is the horizontal, then this is 10 degrees. Now I think they have it where it is possibly to scale. I don't actually think it's to scale now that I look at it. But you know me, I never actually draw anything to scale. So I've got another one down like this, which is 29 degrees. Again, since it is below what we would normally term the x-axis, straight to the right, I would call this negative 29 degrees, but since I'm drawing it down beneath, 29 degrees is plenty good. 382 newtons. The first question is, what is the magnitude of the resultant of these two forces? They're looking for the net force, the total force acting on the car, the combination of both of these. Now, these are vectors, so as we're going to see, we're going to have to draw them as vectors and add them as vectors. The magnitude means simply the number. Part 2 is going to be the other part of the vector, which is the direction. Now, I've got a pretty good drawing here, and you could probably go based just off of it, but I still recommend drawing a free body diagram for whatever you're looking at. That way you're not confused by all the numbers that might be in there. What I'm going to do is I'm going to draw my free body diagram, and I'm going to draw my two forces. I need to name them something. It doesn't really matter what I name them, so I'm going to call this first one FA, and it is 444 newtons at 10 degrees. The second one is down here. I could call it FB, and it is 382 newtons at 29 degrees, technically negative. Now here's where we're going to have a little bit of overlap. I have an x component for FA, FAX, and I have an x component for B, FBX. I also have a y component. I drew my x component for B a little too long, my apologies, FBY, and I have a y component for A, FAY. Now I'm going to need to apply Newton's second law on this in order to find out what the total resultant force is going to be. Now, that means I'm going to have to add up vectors, and as we've talked about many times, we add vectors by breaking them into their components, adding the components, and finding our resultant. So, a first step on this is going to be to take FA and FB and break them into components. Now, I've got quite a few videos. You can check back on my vectors playlist, where you can see me breaking down vectors into components. This is a triangle, so we would use trigonometric functions. We know the hypotenuse and the angle. The x component is going to be the adjacent side for both of them. It touches the angle, we know. And the y component is going to be our opposite side. It's across the triangle for both of them that we know. I'm going to save a little bit of time, and I'm going to start filling in some of these without actually drawing each of the individual calculations that I do. Oh, I buried my calculator. Okay, so I've got cosine 10 degrees times 444. Not in one line, but I actually use two if you follow exactly what I've got there. My x component comes up to 437 newtons for A. FBX, the x component for B, is going to be cosine 29 degrees times, so I found that number, now I'm going to multiply that by 382. I get 334 newtons. To three significant figures, you have a little bit more in there. Now, both of these are to the right, so both of them are positive. I'm going to fill in my y components as well, fay. Now this one is going to be positive because fay is up. I've got 444 times sine of 10 degrees. And I end up with, 77.1 newtons. Fby, my y component for b. Now I'm going to do 382 times sine of 29. I get 185 technically 0.2, but remember, this one is down. I need to keep track of the direction, so that's negative 185 technically 0.2 newtons. I'm keeping everything to 3 significant figures. As long as you do that in each step, you should have an answer that the online system will accept. You are welcome to keep it to more significant figures and increase your likelihood, but 3 is what I've recommended for the class, so I stick with that. I'm going to do my sum of forces in the x direction. Okay, well that's going to be Fax plus Fbx, and those two together are going to be equal to my mass times my acceleration in the x. So, oops, too far. I'm going to have 437 newtons plus 334 newtons equals my mass, which they said was 3,207 kilograms, times my acceleration in the... Oh, I apologize. They don't ask for the acceleration in the first one. They simply ask for the net force. So this is going to give me my total x component. I get so used to solving Newton's second law that I immediately jump into Newton's second law. But they're not asking for the acceleration, which is what I was about to find. They're asking for the total force. Well, these are my components, and so I'm going to add these guys up. These are both in the x direction, so 437 plus 334. I end up with 771 newtons. My total force, the x component of it, is 771. Now I'm going to find my total force in the y. I'm going to add those guys up. We had 77.1 plus a negative 185. Both of these are newtons. Now it's negative because my y component for b is down, so these are working against one another. I add these together, and I've got 77.1 plus a negative 185, and I end up with negative 108 newtons. It's technically 107.9, but again, I'm keeping things to 3 significant figures. You wouldn't necessarily normally round at that point, but I'm trying to, the reason that we do 3 significant figures is so I don't have a whole bunch of numbers tagging along with what I'm doing. So, we're almost done. We now know our x and our y component for our total force. My x component is a positive 771 newtons, and my y component is negative, that means down, 108 newtons. Now I didn't put negative here because the negative means down, and I've drawn it down. I'm keeping track of that information. It makes it a little bit easier when you go through and solve things with the calculator. Now we can find our total force, which is what we're looking for. You can use Pythagorean theorem. 771 squared plus 108 squared. Again, even if I have this as a negative, when I square it, the negative goes away. And then I'm going to take the square root, and I end up with 778.5, which I could call 779 to 3 significant figures. Let me double check what we've got. 778.9, that would round to 779. It will accept 779. In my case, once again, your numbers are likely going to be a little bit different, but it is the exact same procedure. Now that was a lot of work for part 1, but part 2 asks for the direction. If the angle is above the x-axis, they ask for it positive, and if the angle is below, they ask for it negative. Well, we can see our angle right here, theta, is actually going to be below. We can now go through and apply a trig function. And this is where if you have the negative 108, it might give you a weird result. It might give you exactly what you're looking for. I don't actually keep track of it because I learned this way, And if you know how to apply it, you never have to worry about the calculator giving you something weird. All right, let's see. I need the inverse tangent, TOA, opposite over adjacent. So I'm going to do the inverse tangent of 108 divided by 771. We should end up with theta, my direction, is equal to negative, because it's below the x-axis, 7.97 degrees. Let me check what my answer is actually listed as. Negative 7.977 degrees. This is our result. Now we're almost done. The last thing they ask is, if the car has a mass of, my number, 3,207 kilograms, what magnitude of acceleration does it have? And it tells us we can ignore friction. Well, we just found the net force acting on it, and they're asking for the magnitude, so they just want the number of the acceleration. It turns out the acceleration is going to be in the exact same direction as the net force. So the last part is almost done as well. We know that our total force, all together, acting on the car, from the two people pulling it, is 779 newtons. And that is going to be equal, because this is my net force, it's all the forces added together, that's going to be equal to my mass times my total acceleration. We're just finding the number. The direction is actually going to be in the same direction as the net force. Well, 779 newtons equals 3,207 kilograms times my acceleration. I divide both sides by 3,207 kilograms. And I end up with an acceleration of 779 divided by 3,207, 0.243 meters per second squared. 0.243 meters per second squared is what the answer is. All right, this is how you go about it. And once again, it ties into what we have talked about before. Draw your free body diagram, draw your forces coming off. Apply Newton's second law. We're finding the total force here. We don't actually need the MA yet. We're just adding the forces. Forces are vectors, so we have to split them into components. We add all of the x's, and that gives us our total in the x. We add all of the y's, and that gives us our total in the y. And then we can use each of those components to find our resultant. The magnitude is the number, the direction is the angle, at least with this notation. And then once we know the total force acting on it, we can find the total acceleration. The magnitude is this, and the direction will actually be the same way that the net force points.